Okay. Okay, so when we consider a loop, and then in this case, the source of this curve and target of the curve is the same. I call this point V. This is usually called the base point of the loop. And then the gauge transformation of this holonomy, it is just the conjugate of this holonomy by using the same group element. Okay, and then suppose you consider you define a variable which is trace of H, trace of HE, right? And then you can see that its gauge transformation it is a trace of the sandwich GVHE and GV inverse, and you find that, but when you take the trace, this GV will cancel this GV inverse. Yeah, so which means trace of H of E, it is gauge invariant. Gauge invariant. Okay, so that's here you can see that because holonomy transform nicely under gauge transformation, so you can, that's why we use holonomy. That's actually one of the reasons that we want to use holonomy in gauge theory, right? And the holonomy or Wilson line is a very useful variable, very useful observable in gauge theory. Yeah. And especially here you can see that this quantity, when you take the trace, if you consider loop and if you take the trace, and it is a gauge invariant quantity. Yeah, this is or more precisely SU2 gauge invariant quantity, and this quantity this is called a Wilson loop. This is called a Wilson loop variable. This is called Wilson loop variable, and the previous on the curve or on the edge, this quantity we call a Wilson line variable. Over there, it is not gauge invariant, but this quantity which we consider loop, it is a Wilson loop variable. But this is the reason why we call our quantum gravity theory loop quantum gravity. The reason is that historically, people invent the quantization scheme for Ashitaka variable. In that scheme, people use Wilson loop variable as the fundamental variable, right? Right, and then since since the theory developed for almost 30 years, people use less and less. It turns out people use less and less Wilson loops, but more on Wilson lines. Yeah, use more use variable more often, use more often Wilson lines instead of Wilson loops. So although the name of the theory is called loop quantum gravity, but later on it turns out we use less and less loops. Okay. Okay, so here it is the you see some advantage of using holonomies because the gauge transformation is very simple. Yeah. So also if you connect those connecting curves and taking inverse of curve, and the holonomy also transform nicely. Okay, so these are 4 important results of holonomy. So well, this is your homework to prove them. Prove 1, 2, 4 because they are really simple. It's very simple to prove them. Well, to really simplify your work, I give you some hints. So so if you prove 1, 2, and 3, you're proving these 3 properties. You should use the formula 2. You should use the second formula for the holonomy. This is much more convenient to prove property 1, 2, and 3. Okay. And if you want to prove 4, the last property, okay, and this last property is very much convenient if you use the property 3. So after you prove the property 3, and you can use this result, the property 3, to prove property 4. Use property 3. Okay, so these are the most convenient, most efficient way to prove this theorem. Okay. this procedure, and this theorem is very easy to prove. Okay, so yeah, these are all for holonomies. And let me introduce the second lattice variable, what we call gauge covariant flux. Okay, so let's talk about this gauge covariant flux. Okay, so how to define it? Flux, what we call Pj of E. Okay, so it is a little bit more complicated than holonomy, as we will see. So now let's come back to our spatial slice and the lattice. So this, suppose this is our spatial slice sigma, and this is the lattice we have built. Yeah, I make this lattice very coarse, but it's kind of exaggerating. Yeah, the lattice should be very refined in the end. Okay, so now once we have this lattice is what we call gamma. Okay. And once we have the lattice gamma, we can build so-called dual lattice. What is the dual lattice? Dual lattice is, when I draw it, you will see you will see the pattern of the dual lattice. So the dual lattice is basically some lattice which well, intersecting those edges. Well, the face of the dual lattice intersecting with the edges in the original lattice. So what I'm drawing in dashed blue lines, they are called dual lattice. So this dual lattice is what we call gamma star. So this, gamma, this is the cubic lattice, and gamma star, it is the dual lattice. Okay. Well, how to see how to really understand this dual lattice? I think it's enough to draw pictures so that you can easily get what is the dual lattice. So let's zoom in just a single vertex V. So here, let's say this is vertex V. Let's zoom in the neighborhood of this vertex V, and then this dual lattice is just you know, made a box enclose this V. So here, what I see, what you can see that what I'm drawing is just a two-dimensional picture. What I'm drawing is actually a two-dimensional lattice and two-dimensional dual lattice. But actually, sigma is three-dimensional. So which means what I have suppressed the one dimension down. So therefore, we have to draw some three-dimensional picture. So let me try to draw a three-dimensional picture. Okay, so this is a 6-valent vertex. So every vertex is 6-valent, yeah, and it's a cubic graph. And then in the dual lattice, so here on the original lattice gamma, you have edges, right? And however, here at each edge, you intersect each edge by using a so-called dual phase. So here you have a phase intersecting the edge, right? So this is a phase in the dual lattice. And then you make this kind of intersection for all edges, right? So here you get a surface of the cube because you have 6 edges and you cut those 6 edges by using phases. And then phases, of course, intersect. Maybe I use solid line, solid good line, so we can see it better. I don't know. Okay. So here it's like you have this vertex, and you put this vertex. You made a box, and enclose this vertex. I'm not sure you can see it very clear, but I try. Yeah, So these, you can see this edge intersect with the surface in front, and this edge in the back intersect with the surface in the back, and you have all the intersections between edges and the dual faces. Okay. So, and then those dual faces, you can see the dual faces make the intersections, yeah, have intersections, right? And those intersections are edges of the dual lattice. Yeah. So these build the gamma star, the dual lattice. Okay. So this is so-called dual lattice. So why this is called dual lattice? It's because here you can see for each vertex, it is dual to a box. Yeah, it is dual a three-dimensional. So zero-dimensional vertex is dual to a three-dimensional dual box, and an edge in the lattice gamma is dual to a two surface. Yeah, so it's a one-dimensional edge is dual to a two surface, and also, and here you can see that a surface, a face in the lattice. So here I can't draw the entire face, but yeah, if I draw, so here I will get the entire plaquette of the face, and this face is a two-dimensional, and it is dual to a one-dimensional edge in the dual lattice. So that's the reason why we call them dual, because so zero-dimension dual to a three-dimension, two-dimension dual to one-dimension, and one-dimension dual to two-dimension. So here is some basic understanding of this duality. All right. So now to define this gauge covariant flux, and this gauge covariant flux is defined on the dual surface. Okay, this is defined on the dual surface. Okay. So now let's look at the edge and the relation between edge and dual surface. So this is one edge E oriented, and intersecting with this edge, you have a dual surface. Okay, and the intersection point, this is the intersection point, what I call P. Okay, and so this is the source of E, and this is target of E. Okay? And this dual phase is what we call S of E, S sub E. Okay, this is this dual phase. Okay, so given one edge, so this given one edge P, okay, and then and its dual surface, dual phase S of E. So here you can see that every edge uniquely dual to a phase surface S of E. Okay, so and to define the covariant flux, by the way, so what I should mention is that this covariant flux, it is different from, that's why I say it's more complicated than Holonomy variable. The complication is that it depends on, it's a function of both connection and densitized triad. So function of both AAI and EAI. Yeah. So holonomy is a function of AAI only. It's a function of connection only. It's independent of E, but this gauge covariant flux is it's a function of both. Yeah. How to define this function? So here it is. So given the setup, for any let's say X belongs to SE, so which means for any point, I use red color, X, so any point X. Yeah, so we, well, maybe I organize the sentence like this. Okay, so here what we are going to do is that we are going to choose a arbitrary path system. We choose we choose a arbitrary path system on S of E. Yeah. So what is the path system? Namely, for any x belongs to SE, okay, and there exists a path connecting x to the intersection point P. So P is the intersection between S of two surface and edge E. Okay, and now to define the flux. So once we have the path, so here I should illustrate this path. So this is the path. So it means that for any point on the surface, we choose a path from this point to the intersection point P, right? And secondly, we also make a curve from S of E to along the edge to the intersection point P, and then connect the path to this curve. So I define a curve from the starting point from S of E, firstly to the intersection point P, and then using the path system, using the path from P goes to arbitrary point X on the surface. Okay, and this red curve is what we call rho E X. So I define this red curve to be rho EX because it depends on E, because the first part of this curve is traveling along E, and it's also dependent on X because the second part is traveling toward point X. Rho X. Okay, and what is this rho EX? It is a curve from the source of E, firstly traveling to the intersection point P, then following these paths to X, to the point X. Okay, so here now we firstly define a path system on the dual surface, and then we define this curve rho EX. Okay, and then once we have this rho EX, we can define the holonomy. Yeah, so once we have this rho EX, we can define holonomy of along rho EX, because rho EX is just curve, and once we have connection field, we can define holonomy on this curve. Okay, and then with this setup, we can write our gauge covariant flux. Gauge covariant flux P capital PJ E. So this is defined to be minus 1/2 beta. This is some conventional factor. And trace tau j relates to Pauli matrix, and you have surface integral on the face, and then epsilon ABC. So you have this integral along the dual surface. So here, these ABC, they are not anymore abstract index. So here, I just take ABC as a coordinate index because I'm running out of index. So IJ, they are always Lie algebra index. So I have to use ABC for the coordinate index. and then you have H rho E X. Yeah. So multiply the E variable. Okay, so the flux is related to E. So this is the E field, the densitized triad field located at, evaluated at point X. And then the holonomy along the path units. Okay, and that's it. Okay, you see, it looks a little bit complicated. Yeah, so, but it's also easy to understand. It is just sorry. X, and then with tau k. It's a matrix, so sandwiched by matrix by holonomy. Okay, so here you can see this is just expressing the densitized triads as the Lie algebra, matrix in SU2, and then this is just the joint representation, a joint action of SU2 group on SU2 Lie algebra, right? And you have learned a little bit of Lie algebra. This is just a joint representation. Well, but otherwise, if you have no much experience on Lie algebra, you can just view this is a matrix because tau k is a matrix. Yeah, so this is a matrix, and then yeah, it's a matrix multiplication. H multiply this matrix, and then this H inverse, sometimes called conjugate. Well, the result is a function. Yeah, it's a matrix valued function, and we integrate this function on the surface. Yeah? And here you are always integrating a two form because surface is two-dimensional. You are integrating a two form. Okay. And this expression, it is a well, first, the good part of it is that it is a coordinate independent. Although I write it in terms of coordinates, but this is really a coordinate independent formula because this is just equals to well, 1 over well, up to, let me say, up to a coefficient, no, even not up to a coefficient, 1 trace tau j integral SE let me see, right, integral SE and H and this rho E X. And here, this is E. You can consider this EC contract with epsilon ABC dxa wedge dxb. So this is nothing but the dual of E. EC dual of E as a two form and matrix value two form. So here we use E to be EC to be ECK. Okay, yeah. So then this is just a star E and X. So again, a matrix, and then H rho E X. Yeah. And in our previous class, we learned what is a star, and star, of course, is doesn't depend on the coordinate, right? So here is star E. It is just epsilon ABC DC. Right. So star E. So here the star E it is a two form. Well, here I'm using abstract index again. I consider AB as the abstract index, and then star E is a two form. I call star E AB, and this is just epsilon AB C EC. Right. So, and then well, this, yes, and this is not depending on any coordinate. And so in the end, this integral is coordinate independent and independent of choice and any coordinate. And so this gauge covariant flux is also independent of any coordinate choice. Okay. Okay. So this is the explicit expression for gauge covariant flux. And sometimes, especially later on when we do semi-classical analysis, so we will also use a dimensionless version of gauge covariant flux. The reason is that this PJE is dimensionful. So PJ, the dimension is L squared. Yeah. The reason is that you have a two-dimensional integral. You have a two-dimensional integral. So the dimension of P is the area. Well, but the dimension of holonomy it is one. It has no dimension. The reason that it is exponential. So holonomy is exponential. Then the result must be dimensionless. Okay. So, but this flux is dimensionful. So sometimes it is useful to define a dimensionless flux. Dimensionless flux. So lowercase p, PJE. Well, the definition is very simple. It is just a evaluation of capital P, dimension for P at certain unit. And I divide by a squared, and this a is a length. A is also of length dimension. Okay, a is of length dimension. Okay, and so here this a is just a unit, a length unit. Well, and for example, you can take this a is just 1 millimeter. So therefore, this dimensionless p, this lowercase p, is just the evaluation of capital P at 1 millimeter. Okay, so this is the definition for the flux. Yeah, again, it has several useful properties. Okay, so number one, so what we call gauge covariant flux, it means that this is gauge covariant, of course. Covariant, what we mean by gauge covariant is that it transforms, and the gauge transformation is transformed nicely. So PE, so you can define the matrix value of P just by PJ E tau half. Okay, and this quantity it belongs to Lie algebra because tau J is the basis in the Lie algebra. SU2, the lowercase SU2 is in the Lie algebra, and under gauge transformation. Gauge transformation. Well, gauge here, the gauge transformation, you have to take into account both gauge transformation of A and gauge transformation of E, because this is PJ is a function of both A and E. Okay, so you have to take into account both gauge transformations, and this is something we have seen before. So A transformed to GA G inverse plus G partial G inverse, and E transformed to just the G inverse.
For the first and the last, it be partial minus?
Partial, what? Probably there's a minus. Let me see our conversion. Yeah, so this is a minus.
Oh, yeah.
This is minus.
Okay.
Yeah, so this is something we have seen before, I think. So you just apply this gauge transformation. So here you can see that these both A and E, they transform under adjoint representation. So A is transformed like a connection, and this E is just the transform in the adjoint representation of SU2. if you view E as the algebra element, right? And under the gauge transformation, you can see that after you plug in this formula, you can see that this P of E also transform in a joint representation. So you will get just P E transforms to G source of E, E and G source of E in this. So you see that the gauge transformation only depend on it only depends on gauge transformation located at the source of E. So look at this point. So it is, you can see this is just the starting point of this holonomy rho of E. So it matters. So the gauge transformation, so it's different from holonomy. Holonomy is connecting one edge, connecting one vertex to another coordinate, another vertex, and then the gauge transformation is the gauge transformations relates to the gauge transformations at these two vertices. This is the gauge transformation of holonomy. But gauge covariant flux, it only relates to gauge transformation and the single vertex, which is the source of E. Okay, so namely, so PE transforms as a vector, in the joint representation. Representation of SU2. Joint representation of SU2, or equivalently, or namely, E belongs to the Lie algebra SU2, because PE, a joint representation is a representation of a Lie group on its Lie algebra. Right. And this is, well, in case you're familiar with Lie algebra representations, and this is the language to understand the gauge transformation of PE. Well, suppose you are not familiar with representation theory of Lie algebra, then you just view this is kind of multiplication of matrices. So all of them are 2x2 matrices, and gauge transformation is just a multiplication of matrices. And okay, so again, this will be your homework to prove them. Well, I give you a hint. This is very easy. Again, very easy to show. The gauge transformation is really like this. Well, the hint to prove this is just using gauge transformation of E and holonomies. And so E, K. So you can see that the flux depend on two gadgets, two kinds of gadgets. Firstly, this E CK times tau K. This is a matrix. And secondly, this holonomy. Yeah. So flux also depend on holonomy of the path. Okay. So you just need to plug in the gauge transformations of these two gadgets. One, two, E X. Yes, and this holonomy of the path is transformed just like holonomy of path. Source of E. X. Yeah, so this will be the target of this path. Yeah, but the target of the path is just the point X. Right. So here from this figure, you can see that the target of path is just the point X, yeah, and the source of the path is here. and it's a holonomy of along this curve only depend on gauge transformation at these 2 points, and this E gauge transformation of this E only relates to the gauge transformation located at this axis. And if you plug in the formula, you can see these transform just like conjugate, and H transform. Well, you have a group element here, you have a group element here, and two group elements here coming from H and coming from E will cancel. And similar here, these will cancel, right? And then you only left with gauge transformation in front of H and after H inverse, right? And this is what you will get for gauge transformation for the covariant flux. Okay, so you just simply plug in formula and straightforward calculation. Very simple calculation. So second property is about the continuum limit. Okay, so if so what is the continuum limit? So if we set up a coordinate length of the edge, coordinate length of E, well, and coordinate area of SE are mu and mu squared. Okay, so what is the coordinate length? So here, well, on the surface, on the hypersurface sigma, we can build a coordinate, arbitrary coordinate. For example, it's simply the coordinate is the coordinate adapt to this lattice. So we will say they are coordinate x, y, and z, and the lattice edges are go along x